Electric current is the directed motion of charged particles. That's how we are taught at school. And in most cases, this works. In metals, current is carried by electrons. In electrolytes, by ions. In semiconductors, also by holes. But if you ask a physicist, what is electric current really? The answer may surprise you. The fact is that modern physics still does not have a single fundamental description that explains the nature of current equally well in all media, from ordinary wires to quantum materials. We are excellent at measuring current, calculating it, and using it in technology, but understanding is not the same as control. Let's take the simplest metallic conductor. According to the classical model, free electrons begin to move under the influence of an electric field, and a current arises. But then a question appears. If the field accelerates the electrons, why doesn't the current keep increasing with time? The usual answer is that electrons constantly collide with the atoms of the crystal lattice, lose energy, and as a result, a steady average drift velocity is established. This model works beautifully in practice. But it remains an approximation, a convenient description, not a complete picture of the microscopic processes. It becomes even more interesting if we recall that, in a steady state, the bulk electric field inside an ideal conductor tends towards zero. So what maintains the ordered motion of charges? What force is pushing the electrons if there is almost no field inside? Here again, we run into not a lack of calculations, but the limits of our intuitive explanations. The situation becomes even more complicated beyond familiar materials. In so-called strange metals, current behaves in ways that standard theory does not predict. Experiments show that it flows smoothly, without the fluctuations one would expect if current always consisted of discrete individual particles. In such systems, current is increasingly described as a collective phenomenon, where the usual picture of electrons as independent particles stops working. In addition, physics offers different approaches to how electromagnetic interaction is transmitted. Modern theory relies on the concept of local action. Energy and momentum propagate through a field that fills space. Yet even within this framework, our physical intuition about how energy transfer actually happens, especially in quantum systems, remains incomplete. The mathematics works flawlessly, but intuition lags behind. And here lies the paradox. We create ultra-precise microchips, build power lines thousands of kilometers long, send spacecraft to distant planets, and develop quantum computers. And yet we cannot give a universal answer to the question of what exactly carries electric current in every possible medium. After all, the carriers of current are fundamentally different. In some cases, they are electrons, in others, ions, in others, holes, and in still others, collective excitations that are not even particles in the usual sense. And in superconductors, current flows without resistance at all. We describe this using Cooper pairs and can accurately predict the system's behavior. But the deep reason why exactly this form of collective motion is possible remains more mathematical than intuitively clear. That is why defining current as the directed motion of charges is a useful generalization. It works well for engineering and education. But behind this simple formulation lies a multitude of different physical mechanisms that cannot be reduced to a single universal process. And there is nothing wrong with that. Science is not obliged to have final answers to every question. Its strength lies in honesty about the limits of our knowledge. We do not know what electric current is in the most fundamental universal sense. But it is precisely this lack of knowledge that drives physics forward, beyond models, analogies, and school definitions. Because sometimes the most ordinary things, like a light bulb being switched on, turn out to be windows into some of the deepest mysteries of modern physics. So the next time you turn on the light, think about it. What is really happening in those wires? What exactly is moving there? Or is anything moving at all? If this topic caught your interest, write in the comments what surprised you the most. Do you think science has already figured everything out about electricity? Or on the contrary, that we are only approaching a true understanding? And if you want more episodes about familiar things that hide fundamental mysteries, be sure to subscribe to the channel. Coming up next, why temperature can be negative, how current can flow without electrons, and what lightning has in common with quantum entanglement.